important term in magnetism which is related with the Bohr's theory of hydrogen atom, and that is called as Bohr Magneton, which is called as Bohr Magneton. Now to find the value of Bohr Magneton, we have to write again the equation for orbital magnetic dipole moment, and which is equal to MO equal to 1 by 2 E divided by ME into LO, which is equal to 1 by 2 E divided by ME into LO, angular momentum of revolving electron according to second postulates of Bohr theory. This angular momentum is n into h divided by 2 pi. So the value of angular momentum according to the Bohr's second postulate is integral multiple of h upon 2 pi. Then we get this is equal to E into N into H divided by 4 pi m into suffix E, that is mass of electron. And the Bohr magneton is nothing but the minimum magnetic dipole moment of revolving electron, and for minimum magnetic dipole moment of revolving electron, the value of N is taken to be 1, and therefore MO, that is minimum, that means Bohr magneton, the formula is MO minimum is equal to E into H divided by 4 pi into M suffix E, that is mass of electron. Now, if we substitute the values of charge on electron, H, which is the Planck's constant, pi and mass of the electron, then the value of this Bohr magneton is come out to be 9.27 into 10 to the power minus 24. So this is the value of Bohr magneton, which is 9.27 into 10 to the power minus 24 ampere meter square. So Bohr magneton, to find the Bohr magneton, we relate or we combine two chapters. One is the magnetism and one is the atom molecule nuclei from 12th standard. And therefore, we get Bohr magneton, which is the minimum orbital magnetic dipole moment, and whose value is 9.27 into 10 to the power minus 24 ampere meter square. Next, we find the different forms of orbital magnetic dipole moments. First of all, we have already found that MO is equal to 1 by 2 into E into V into R. Now we will find another formula. If we substitute the value of V, as we know that V is equal to R omega, therefore this equation becomes MO is equal to 1 by 2 E into value of V is R omega into R, and which is equal to 1 by 2 E into omega into r square. So this is the second form of orbital magnetic dipole moment in terms of angular speed, where omega is the angular speed. Again, we find another relation which is related with kinetic energy of revolving electron and magnetic field induction. Then for that we consider, suppose that electron is revolving in magnetic field perpendicular to the magnetic field, then it performs circular motion. And when electron is revolving in circular motion in perpendicular magnetic field, we know that the centripetal force is equal to force due to magnetic field. Now, the centripetal force, as usual, we know that, which is mv square divided by r. Again, force due to magnetic field is E into V into B. And we write, if we multiply both sides by half mv square divided by r is equal to E into V into B. Then half mv square is called as kinetic energy, and this force due to magnetic field becomes E into V into B, and we write this equation as mv square divided by r is equal to force due to magnetic field, which is equal to E into V into B, and half into mv square divided by B is equal to EVR, again here multiplied by half on both sides, and therefore again we found new formula, as we know that the half mv square is called as kinetic energy, and the right hand term half EVR is called as orbital magnetic dipole moment. So another formula is MO is equal to kinetic energy EK divided by B. So this is the another form of orbital magnetic dipole moment. So today we are studying three different forms of orbital magnetic dipole moments of revolving electron. First one is called as MO is equal to half EVR. Another formula is MO is equal to half E omega r square. And third formula is MO, which is equal to EK divided by B. Then in relation with today's two articles, we are going to illustrate some examples on this. And the first example on this revolving electron, which possesses magnetic dipole moment, is if you are given specific charge which is equal to 1.76 into 10 to the power 11 coulomb per kilogram. you have given the value of angular momentum, which is LO, and its value is given 2 into 10 to the power minus 34 kilogram per second. And from this data, we have to find the value of orbital magnetic dipole moment. Then in this example, student must know the meaning of specific charge. The specific charge is nothing but the ratio of charge on electron and mass of the electron. That means this specific charge is nothing but E divided by ME. And as we know the formula or the relation MO, which is equal to E divided by 2 into Me into LO. So the value of orbital magnetic dipole moment comes out to be 1 divided by 2 into E by ME, which is nothing but the specific charge, and its value is 1.76 into 10 to the power 11. And LO, which is the angular momentum of revolving electron, and its value is 2 into 10 to the power minus 34 kilogram meter per second. And if we calculate this, we find the orbital magnetic dipole moment, which comes out to be 1.76 into 10 to the power minus 23, and unit of magnetic dipole moment is ampere meter square. So this is the one of the illustrative example on the article as we have learned today, that is the relation between orbital magnetic dipole moment, angular momentum of the revolving electron, and the specific charge, that is the E by M ratio. So this is one example. Now again we take another example related with magnetic dipole moment, and that example is, suppose that the electron is revolving around the nucleus having a radius, and its radius is 0.5 angstrom unit. So R is the radius of the orbit in which electron is revolving, which is 0.5 angstrom unit. And as the electron is revolving, it possesses the frequency. It possesses the frequency which is called as nu or n, and its value is 10 to the power 10 megahertz. And again we have to calculate orbital magnetic dipole moment or magnetic dipole moment of revolving electron. So we have provided radius and we have also provided the frequency. Then to solve this example or numerical, we know that magnetic dipole moment is given by the formula originally or initially I into A. Again we know that I is equal to E divided by T, and area is equal to pi r square. Again the reciprocal of time period, that means this 1 by T, is called as frequency, and therefore the formula becomes E into F, that is frequency, into pi into r square. So this is the another form of magnetic dipole moment. M is equal to Ia, and I is equal to E by T. Again, 1 by T is nothing but the frequency, and we get new formula. M is equal to EF into pi r square. And by using this formula, we will solve this numerical. And in this numerical, we have provided frequency, we have provided radius, and we know the value of charge on the electron, that is magnitude of charge on the electron. So if you substitute the values, the magnetic dipole moment becomes M is equal to 1.6 into 10 to the power minus 19 into frequency is 10 to the power 10 megahertz. That means again into 10 to the power 6. And radius is given 0.5 angstrom unit. Again, we know that 1 angstrom unit is equal to 10 to the power minus 10 meter. And therefore, this radius 0.5 angstrom unit can be written as 5 into 10 to the power minus 11 and bracket square. So as we have substituted the values in new formula for magnetic dipole moment in terms of frequency, capital M is equal to E into F into pi r square. If we calculate this value, then the answer comes out to be 12.56 into 10 to the power minus 24, and unit is ampere meter square. So I hope student satisfied with explanation given to this numerical, as in our textbook only we have proved M is equal to half into EVR, but by using different formulas we can calculate or we can solve large number of numericals or MCQs given in the textbook or in the examination. So this is the second numerical we have solved today. Today we are going to solve again one numerical which is related with today's article, that is magnetic dipole moment of revolving electron. And the numerical is, suppose that the electron performs UCM, uniform circular motion, in magnetic field. That means magnetic is perpendicular, and the value of this magnetic field is 1.2 Tesla. And in this case, the kinetic energy acquired by the electron in the orbit Ek, and this value Ek is equal to 6 into 10 to the power minus 20 joule. And again we have to calculate magnetic dipole moment. So to solve this example, we have to use the formula magnetic dipole moment or orbital magnetic dipole moment, capital M, which is equal to, we have already learned how the new formula, which is Ek divided by B. So orbital magnetic dipole moment is kinetic energy of revolving electron divided by magnetic field, and if we substitute the values of kinetic energy and magnetic field. The value of kinetic energy is 6 into 10 to the power minus 20 joule divided by the value of magnetic field is 1.2 Tesla, and if we solve this, we get the value of orbital magnetic dipole moment, which comes out to be 5 into 10 to the power minus 20, and unit for magnetic dipole moment is ampere meter square, or we write another unit from this formula. Orbital magnetic dipole moment is equal to energy upon magnetic field. So another unit for this numerical or this answer can be written as 5 into 10 to the power minus 20 joule per Tesla. So this is the answer for the third numerical we have taken today, which is electron performs uniform circular motion in magnetic field perpendicular magnetic field, and its kinetic energy is given, and we have calculated its orbital magnetic dipole moment by formula m is equal to Ek divided by b, and which comes out to be 5 into 10 to the power minus 20 ampere meter square, or new unit is joule per Tesla. So today, up till now, we have studied circular coil carrying current behaves like a magnetic dipole, and second part we learn about orbital magnetic dipole moment and the orbital magnetic dipole moment of revolving electron, and third we learn about gyromagnetic ratio. Now, if someone asks to find the value of equivalent current in orbital motion, suppose that the electron is revolving around the positively charged nucleus with angular velocity omega having radius r, and as we know that the revolving electron is equivalent to current flow. The direction of electron is anti-clockwise, therefore current flows in the loop in clockwise direction. And if we want to show the value of this current in this coil is given by I is equal to E square divided by square root of 16 pi cube epsilon 0 me into r cube. So as the electron is revolving in circular orbit around the positively charged nucleus or around the proton with angular velocity omega, then equivalent current in this circular loop is given by I is equal to E square divided by under root of 16 pi cube epsilon 0 me into r cube. And to show this, we must know first of all the value of omega square or omega. Then to find the value of this omega or omega square, we use the first postulates of Bohr's theory of hydrogen atom. and from that electrostatic force of attraction 1 upon 4 pi epsilon 0 E square divided by R square is equal to centripetal force, that is mv square divided by R. Now in this case, this 1 R gets cancels with this R. And in next step, we write again 1 upon 4 pi epsilon 0 E square divided by R, which is equal to m into V, as we know that this V is equal to R omega, so R square into omega square. Here we write as V is equal to R omega. So in first postural equation, we substitute the value of V, which is equal to R omega. And after solving this, we get omega square is equal to. So omega square is equal to 1 upon 4 pi epsilon 0 into E square divided by M into R cube. So this is the value of omega square, which is equal to E square divided by 4 pi epsilon ME into R cube, or simply M into R cube. So we know the value of omega square. Our aim is to find the value of equivalent current in the circular loop, which is given by this formula. So first of all, we have to find the value of omega square, and from that we can write the value of angular velocity. Again, to find the value of I, to show, our aim is to show this equation. So I is equal to E divided by T, which is equal to E divided by T is equal to 2 pi R by V, which is equal to E into V divided by 2 pi R, which is equal to, again, V is equal to R omega. Therefore, we write E V is equal to R into omega divided by 2 pi R, and in this case we cancel this R with this R, and our formula for current is E into omega divided by 2 pi. So current is given by the formula I, which is equal to E omega divided by 2 pi. So this is the value of current. Now in this value, if we square this, both the sides, then I square is equal to E square omega square divided by 4 pi square. And we are very near to the shore. Substitute the value of omega square, as we have already proved. Omega square is equal to 1 upon 4 pi epsilon 0 E square divided by M suffix E into R cube. So I square is equal to E square divided by 4 pi square into value of omega square is 1 upon 4 pi epsilon 0 E square divided by M suffix E into R cube. So the value of omega is substituted 1 upon 4 pi epsilon 0 E square divided by M suffix E into R cube. Now we get I square, which is equal to E square into E square, which is E raised to 4 divided by 4 into 4, which is 16, into pi square into pi, which is pi cube, again epsilon 0, again m suffix e and r cube. So value of I square is e4 divided by 16 pi cube epsilon 0 m suffix e r cube, and therefore I is equal to, if we take square root on both sides, then this I becomes e to the power 2 divided by the denominator value is in under root, which is 16 pi cube epsilon 0 me and r to the power 3. And our aim is to show the orbital current is given by the formula I is equal to e square divided by under root of 16 pi cube epsilon 0 me r cube, and we have succeeded in showing this. So to show this value, we have to first of all find out the value of omega square, and that value of omega square is substituted in the equation for current, and then we get the value of current, which is I, which is equal to e square divided by under root 16 pi cube epsilon 0 me r cube. Again, lastly, by using this value of current, we can show again orbital magnetic dipole moment. And to show the orbital magnetic dipole moment, we know that the value of orbital magnetic dipole moment MO is equal to IA is equal to I into pi into r square. This is the value of magnetic dipole moment. And if we substitute the value of this I, then we get MO is equal to E square divided by under root 16 pi cube epsilon 0 ME into R cube into again pi R square. Therefore, if we square on both sides, MO square is equal to e to the power 4 into pi square r raised to 4 divided by 16 pi cube epsilon 0 me r cube. And therefore, final result is MO, which is equal to e to the power 2 divided by 4 into square root of r divided by pi epsilon 0 into me. So magnetic dipole moment of revolving electron again given by this new formula, which is MO is equal to E square by 4 into under root R divided by pi epsilon 0 me. So today we have studied two articles from magnetism. First one is circular loop behaves like a magnetic dipole, and magnetic dipole of revolving electron. Thank you.